Bismillahirrahmanirrahim. Very good day. So now we are on chapter 5, the law of motions. Okay, whereby previous lesson we've learned about how to define an object in objective manner. Then it brings us to how the object is in motion or is it stationary. How to describe about the motion of the object, whereby we've learned about the speed, the displacement, the position, the acceleration, the instantaneous velocity, the instantaneous acceleration, the average of them, many things about on how the object is in motion. Then now we are going to focus more on how about the one that causes the motion, right? Where we will begin with the force. The force is actually the one that causes the motion to take place, as we discussed before. So the concept of force, we have two kind of in general, where we have a contact forces, okay, whereby there is a physical contact between the force and the object being applied, the force on it, right? There is a physical contact, so we call it contact force. And another type of force is field force. Okay, as we know, there is no physical contact between two objects, the one that applying force and the one that being applied the force onto it. All right, so for example, when we have two objects having masses, okay, based on Newton gravitational law, okay, these two objects going to have attractive forces between them. Okay, there is no physical contact, but the force does exist. And between two charges, right, between two charges, whether it's same sign, positive and positive, or like this example, negative and positive, there will be a force. Okay, could be if there are different sign, attractive force. If it is the same sign, then repulsive force. There is no physical contact, but yet, yes, there is a force acting on both of the object. And this is magnetism, whereby this is magnetic bar, okay, the ions, okay, going to feel experience being pulled towards the north pole of a magnetic bar. Then, okay, we're going to measure the force by using certain tools, where in this example we have a downward force F1 applied to the spring scale that causing elongation of the spring of 1 cm. Now we are applying F2 on the same spring, okay, downward still, but the elongation right now is 2 cm. And now if we combine these two forces on the spring, okay, we are going to see the elongation of the spring going to be 3 cm, right? So that if the applied F1 and F2 in the same direction, how about if the F1 and F2 not in the same direction applied to the spring scale? So for this concept, okay, we are going to use a vector concept or technique or method to solve, to account for the resultant force, okay, acting on the object or our spring scale here. So for this case, let's say we are applying F1 downward, okay, and F2 to the right. Right, how to have the resultant by using vector technique. We know that this is a combination. Resultant is actually combination of F1 and F2. So based on that facts, okay, we are going to use Pythagoras, where we are going to combine F1 squared plus F2 squared and square root of this is equivalent to the magnitude of the resultant force, or symbolized as F1. The unit is 2.24. It could be Newton, it could be any other units, okay? But must be a units because it's a vector. And how about the direction of the resultant? Okay, most of the time, we are going to take the direction from the positive x-axis to the right as our positive x-axis and upward as our positive y-axis. So the theta is from the x-axis. If you are using from the x-axis, then we may use tangent theta. Tangent theta is equivalent to, okay, y component over the x component. This is the original formula. Okay, so the y component over the x component. So what is our y component? Which is F1. This one. And our x component will be F2. So uptangent of this amount will give you 26.6 degree. So when we explain about our resultant, the magnitude of it is 2.24 units at the direction of 26.6 degree below x-axis. So let's move to 5.2, Newton's first law and inertia frames. If an object does not interact with other objects, it is possible to identify a reference frame in which the object has zero acceleration. This is what we call it, initial frame of reference, right? So it means that, for example, what is all about? Okay, if let's say we have an object sitting on a static table, no motion at all. At this situation, okay, we say that the object now is stationary. It is not in interaction to any other object nearby it, okay. So in simple, sum of the F for this particularly object or system must equivalent to 0. This is what Newton's first law. Regarding the initial frames, what does that mean? We are now giving a statement that this object is at rest with the condition that we also being here nearby this, where the whole system, the observer, ourselves, okay, and also the whole bulk of the system here, okay, completely on the same floor. That is why we can say that the object is stationary. Let's say the whole system, okay, including the observer, the table, is actually on a lorry, okay, whereby the lorry right now, okay, is moving with certain acceleration. So with reference to the person, the observer, okay, right now, firstly, on the lorry, whereby the whole system is static, okay, we can have a conclusion that, okay, the object seen by this person, the observer, is stationary. So the first initial frames, okay, of reference is the person. But now, if let's say the whole system is placed on a lorry, then the lorry is moving with certain acceleration. For the second observer, the second observer going to give a statement that the object is not stationary because the object right now is moving, okay, according to the motion of the lorry with certain A. Now, this is our observer. We have a different initial frame of reference. Initial frame means that where are we looking at, from which reference, from which point of view we are looking at the situation. So from which frame? Okay, so means that it depends on which point view we are using. That is the meaning of the initial frame of reference. Now, this is actually the law, the first law of Newton's law. In the absence of the external force and when viewed from an initial reference frame, an object at rest remains at rest, and an object in motion continues in motion with a constant velocity. That is, with a constant speed in a straight line. How is it? Okay, what does that mean by Newton's first law? Sum of F equivalent to 0. How to have, okay, the sum of F equivalent to 0? It could be in a way F1 plus F2 plus F3 plus F4, okay, plus up to Fn is equivalent to 0. This is one meaning of it. Okay, the other meaning of it is, okay, F1 plus F2 plus blah 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 up to Fn is equivalent to Ma, but the A is 0. What does that mean? Okay, what does that mean? The A is 0. Okay, as we know, A is actually delta V over delta T. The delta V is 0. There is a V, but the V is remain the same. As we know, A is defined V final minus V initial over the time taken to have the change. If the V final is the same as V initial, the delta V going to be 0. So means that the object is remaining with the same velocity or same speed. Okay, so with the same velocity, the delta V equivalent to 0, consequent of it, the A equivalent to 0. Okay, that is why within the statement of the first law, also there is a part of this. An object in motion continues in motion with a constant velocity. Okay, whenever there is no external forces acting on it. External forces, the net external forces. It's not only forces, the net. When you do the sum, the amount of it, 0. Okay, this is the Newton's first law. The masses is actually a property that specifies how much resistance of an object exhibit to change in its velocity. So that is how we also define the mass as the character of the inertia. Okay, just imagine this ball is made of iron. Okay, solid iron. For sure, it's very heavy and it's very hard for us to move the ball, isn't it? Compared to the original ball consists of air inside and then rubber outside as a sphere, isn't it? So the mass, the difference in mass, okay, explain to us how big the resistance. Okay, that is why this is also related to the inertia. Okay, because inertia is tendency not to change the motion. Okay, Newton's second law. So Newton's second law says that, okay, if there is external force, net external force applied to an object, okay, the acceleration of the object is directly proportional to the F applied, and the acceleration of this object is inversely proportional to the mass of the object. Combining these two information, we can have sum of F on the object is equivalent to MA. So when you put sum of F, it means that this is actually could be F1 plus F2 plus F3, okay, plus up to F and equivalent to MA. How is it going to happen? There is a possibility that you have another F here, you have another F here, right? You have another F here, okay? Or you have another F here, okay? Like this, right? Okay. So in real, okay, we have to consider all three axes. This is along X, this is along Y axis, this is along Z axis, right? So meaning that when you have frame of reference, right, X axis, Y axis here, you might have F resultant. Okay, for simplicity, let's consider two axes first. Okay, for this resultant force, there is a combination of components. F along X actually combined with F along Y. Then you're going to have this resultant force SF with the direction of theta to the respect of x-axis. Right. Example 5.1, an accelerating hockey puck. Hockey puck having a mass of 0.3 kilograms slides onto the frictionless horizontal surface of an ice rink. Two hockey sticks strikes the puck simultaneously, exerting the force on the puck shown in the figure. The force F1 has a magnitude of 5 Newton and directed at 20 degrees below x-axis. The force F2 has a magnitude of 8 Newton and its direction is 560 degrees above the x-axis. Determine both the magnitude and direction of the puck's acceleration. Alright, so what should we do? Okay, we are going to resolve each of the forces into its components. As we know, okay, for this F1, right, for this F1, we have F1Y and also F1X. Alright, for this F2, we have F2X and F2Y. Right, whenever you want to resolve, you need to see the arrow for each of the component, because the arrow representing the direction and consequence of it, the magnitude of the F going to be written as positive or negative. So for Fy, sum of Fy, okay, must be coming from F1y plus F2y. F1y is pointing downwards. So bear in mind, for F1y, there will be negative sign. Right? Not here yet. Okay, later. Then for F2y, this is F2y is pointed upward. It must be positive sign. And how to get the magnitude of F1y? Okay, is F1 sin theta. Okay, why is it sin theta? Recall back. Okay, this is the sin theta here, 20 degree. So to the respect of this is F1y is the one that we don't know. We want to figure out. F1 is given. This is hypotenuse, right? So to the respect of this 20 degree, F1y is opposite side. That is why we are going to use sin theta. And for F1y, it has negative sign because it's pointing downward. Right, and F2y, okay, to the respect of phi, 60 degree here, is actually opposite side. That is why we're also going to use sin. Okay, and it's positive because it's pointing upward. Based on Newton's second law, sum of F equivalent to MA. So for Y component, we are going to use this one. and this is for X component. Okay, later on we'll take a look on this. So we are going to use Y component firstly. So from here, sum of Fy equivalent to MAY. So AY must be sum of Fy over M. So this is the sum of the Fy. F1 sin theta, negative ya, plus F2 sin phi over M. Alright, so this is about y-axis. For x-axis, right, we are going to apply the same concept. Ax is equivalent to sum of fx over m. And what is the sum of the fx? Is actually f1x, and it's positive because it's pointing to the right. So it's actually f1x, f1 equivalent to f1 cos theta. So the theta is here, 20. And then for F2, okay, for F2, our x component is pointing to the right as well. So it's positive as well. And if F2 cos phi, okay, because to the respect of this angle, okay, F2x is adjacent side. You just put 20 degree also can, no problem. Right? So 5 cos 20 plus 8 cos 60 over the mass is 0.3. Then you will get 29. This is the acceleration along x only. Okay? Now, this is for along y. Alright? For sin, you have to consider this. Whether you put the sign on within the angle, or you also can put it here. You can put it here, negative. Okay, for negative, then the angle, no need to put negative anymore. Right. So if you want to put it negative in front, it's going to be like this. Negative 5 sine 20 plus 80 sine 60 over 0.3. Whether you want to put it like this or you want to put it like this, also the same. Right? Then you will get 17 meter per second squared. This is along y. Okay? Have we done? Not yet. You have to combine. The A is actually a combination of x and y component. Then you're going to use Pythagoras. You will get 34 meter per second squared. And this is the direction of your A. Right? It begins with tangent. Beta is equivalent to AY over AX. Right? So what is your AY? It's actually 17. What is your AX? It's 29. Then you will get 31 degree as the angle for your acceleration, or A. So now, okay, now suppose 3 hockey sticks strike the puck simultaneously instead of only 2. Now we have the third force, right? With 2 of them exerting the forces shown in the figure. Okay, the results of the 3 forces is that the hockey puck shows no acceleration. What must be the components of the third force? If there is no acceleration, means that the object have the total net force equivalent to 0. Because the idea is sum of F equivalent to MA, and now in this situation, the A is 0. It means that the net force, okay, when we sum everything here, the net force must equivalent to 0. Okay? So it means that, okay, we are going to have the F3 components, okay, must be counter back, okay, the component of the one that we calculated before this. Alright, but we can have a long journey to solve it. For the long journey, okay, it's going to be sum of fx for f3x going to be negative, okay, because it's to counter the resultant just now. The resultant fx just now is positive, so must be f3x going to be negative, okay, so that the net will be 0. So negative 0.3, this is a m, this is a a, okay, based on sum of f equivalent to ma, right? So to have the f, now we are using m times a, okay, so the mass times with the a, you will get negative 8.7. This is f3x. f3y also going to be negative because the one that we solved just now, when we combine f1 and f2, we have positive amount of fy, okay, so now f3y must equivalent to negative of y as well lah. Alright, then 0.3 times 17, you will have negative 5.2 Newton. So this is a component of your f3x with the condition that the hockey puck shows no acceleration. The gravitational force and weight. Okay, this is actually quite common for you, right? When we talk about weight, okay, most of you know that this is equivalent to mg, but actually the concept of this is actually the a is the g, okay, the g is coming from the concept of Newton's second law. Gravity, simply known, is actually gravitational acceleration, okay, the a of the earth that always make sure everything going to always falls to the ground, okay. Doesn't matter how many times you jump, okay, how high you are, okay, as long as you are within the gravitational range, okay, then you're going to experience an a, which is a is equivalent to the gravitational acceleration, or simply known as g. Previously you learned this about 10 meter per second square, right? To be exact, is 9.81, right? Or 9.8, also accepted, meter per second square. So that is how we define our weight, right? Okay, so simply put it as Fg equivalent to mg. Okay, I think most of us know that the gravitational acceleration varies with the geographic location, but then with the condition that the position of that location is very, very high from the sea level, like for example on the mount of the Everest, right? Then the G will be varied, okay, reduced slightly in amount, right? However, if the difference only about 100 meters, 500 meters, it's not that much of a difference. Okay, and the gravitational force and weight, if we are on the moon, will be less weight because of the G of the moon is only about 1.6 meter per second squared compared to the earth is 9.8. Right, so to feel weightless, we should go to the moon more frequent. Okay, then Newton's third law. If two objects interact, the force F1, 2 exerted by object 1 on object 2 is equal in magnitude and opposite in direction to the force of F2, 1. What does that mean? Exerted by object 2 on object 1. This is also known as action-reaction. Okay, to simplify this thing, when you have F1, 2, simply put in the middle here the word of on. It means that this is a F okay, the object 1, okay, applied on object 2. The doer is object 1. The one that experience the force is object 2. Must be equal in amount or magnitude, but in opposite direction, okay, of F to 1. That is why you have negative sign here. Okay, so again, put on, okay, between the numbers. Then you will know who is the one that doing the force, who is the one that experiencing or accepting the force. Okay, so if there is a push, okay, there is a reaction. Okay, action reaction. So this is the way we define Newton's third law. So this is how Allah tell us. Okay, if there is action, there must be reaction. If there is good deeds, okay, there must be a bad, okay, deed as well. So you need to learn, you need to know how to manage this. So for example, okay, between two objects here, okay, these two objects going to experience F12 and F21. Okay, so if you see here on how to draw, on how to sketch the force F12, it means the F1 on 2. So attractive force between these two masses. Okay, so attractive force here, so the object 2 experience, okay, and attractive force, okay, attracted to object 1. So this is the way we sketch the force. It means that this object 2 is attracted to object 1. So the one object 1 is attracting, is the one that doing or applying the force on object 2. Okay, goes the same to the object 1. Okay, what does that mean by F21? It means that object 2 is applying a force on object 1. So what happened to object 1? It's going to feel attracted to object 2. That is why we sketch the force is towards, okay, at the center of 1 towards 2, because object 1 is now experiencing an attractive force being attracted by the object 2. Right? So this is one of the simplest application of the Newton's third law. If you see here, there is a monitor, there is a table, okay, and here is the floor. As we know, when there is a touching or contact, physical contact between two objects, must be there is a normal force. What does that mean by normal force? It's a force that is normal to the surface of the touching. So from the monitor to the table, okay, there is normal, there is a contact between monitor and table, so there is a normal force, and this normal force is actually equivalent to force table on monitor. Okay, table on monitor, and this monitor also going to apply a force on the table, so monitor on table, so downward. Okay, just like I push you, you push me back against, right? So, and how about the monitor and the earth? Okay, the monitor going to experience a weight, gravitational force, or also actually known as force on earth, from earth on the monitor. Okay, from earth is doing or applying force on the monitor. Okay, which equivalent to force from monitor on earth. Okay, attractive force. Sum of F must equivalent to 0, because we know that the monitor is not in motion. Okay, sum of F equivalent to 0. So for the monitor itself, okay, it has what? It's experienced what? It experienced normal force upward. It's also experienced force from gravity, or also known as weight. okay, and it's downward. Okay, that is why, okay, we can put it in IJK terms, okay, vector unit terms, right? This is normal force, okay, positive J, and weight is downward or negative J. Some of them must equivalent to 0 because the monitor is not in motion. Rearrange of this, you will have normal force equivalent to the weight. To simplify our calculation later on, we need to do free body diagram. So for the monitor itself, okay, if we isolate the monitor from the table, we will have this diagram. Now simplify this diagram, okay, we are representing the monitor only by a dot. Then we list down all the forces acting on the diagram, on the object or the monitor. So you have normal force and you have weight. This is what we call it free body diagram, whereby we isolate our object and simplify it to simplest version and list down all the forces acting on it.